So how do microorganisms die? How do the chemical and physical methods we use actually kill or damage microorganisms? This can be good to know when you need to make decisions. Sometimes we need to think about using one type versus another, so let's get into it. Mode of action is our term for how an antimicrobial agent works. And there are a lot of different things, and we'll go through them, a lot of different modes of action. Some things to think about. Some agents are very selective. That is, they'll only attack a specific part of a specific type of bacteria. And so those will have a narrow spectrum of activity. We'll come back to this in part 2. We'll look at spectrum of activity. Here, what we're comparing is things like heat, which can inactivate anything. High enough temperature can inactivate anything we're ever afraid of, versus something like penicillin that would only attack gram-positive bacteria. And so let's go through the major modes of action. So cell wall disruption is one of the biggest one among antibiotics. So it's definitely the most common mode of action for antibiotics. And what it does is allows for lysis of the cell, because the cell wall gives the cell membrane the mechanical strength it needs to avoid breaking. And so we will mostly see this one when we look at antibiotics. These are all the antibiotics in the 5th edition of the textbook that affect the cell wall of bacteria. Cell membrane disruption is what we're trying to do when we disrupt the cell wall, but it's harder to do, and bacteria actively protect their membranes. So we have some things like detergents that disrupt cell membranes. We have a few antibiotics that disrupt cell membranes, and then solvents like ethanol disrupt cell membranes. And as you can imagine, if you disrupt cell membranes, the inner contents of the cell will leak out, and that's kind of the definition of a cell being dead. Some of the things we will look at here interact with DNA, or they disrupt nucleic acids. So that could include blocking transcription or translation or DNA replication, and there are antibiotics that do that. There's causing mutations. There are antiviral drugs that do that. But then there are techniques that physically break the DNA. That's like what ionizing radiation does. And if the DNA breaks and the cells have to repair it, they end up getting lots of mutations, and they can usually not survive. So directly attacking the DNA is a great way to kill them. In other cases, more generally, agents will disrupt enzymes. So lots of different things we will look at today denature proteins. And so they slow down every enzyme in the cell if they denature every protein. Things like steam or boiling water just disrupts every protein. And so that means enzymes work slower. It also means like ribosomal subunits stop working, so no proteins can get made. And that's the second most common mode of action of antibiotics. They prevent the ribosome from working. And so generally speaking, if we can disrupt a typical protein, we can really slow down a cell. And if we destroy every protein or physically inactivate every protein, the cell will be unable to recover from that. So that's the 4 major ways that antimicrobial technologies work. And that brings us to kinetics, and this is one of those other topics that I think everyone should know about. So kinetics is the study within any field of how fast things happen and like the timing. So in disinfection, timing is very important. When we kill microorganisms, it's not instantaneous. and it happens, it follows an exponential decay process. So what that means is, in every time interval, like every 30 seconds, the population decreases by a factor or multiple. So for example, every 30 seconds, it decreases by 20%. And then in the next 20 seconds, or the next 30 seconds, it would decrease by 20% of the remaining. Think of it as the opposite of exponential growth. In exponential growth, the population increases by 100% every doubling time, or every generation time. In exponential decay, you get a decrease in a factor every set time. And so for exponential growth, we had to graph things on a logarithmic scale. And for exponential decay, we have to do the same thing. So this brings us to the idea of a decimal reduction time. It's the time it takes to reduce a population by 90%. And the way we think about this is it usually won't be different. If we have, let's say, a tube full of E. coli bacteria and we measure the decimal reduction time, it's going to take the same amount of time to go from 100 cells to 10 as it did to go from 10 to the 7th to 10 to the 6th. That's 10 million to 1 million. So if you reduce a population by 90%, you divide it by 10. It's the same thing. And so we think of it as the decimal reduction time, whether it is from 100 to 10 or from 10 million down to 1 million, or 10 trillion down to 1 trillion. And that's really what exponential decay is. It takes the same amount of time to do this tenfold decrease as it does to do this tenfold decrease. If you're curious, it happens this way because it's based on probabilities. In any given time, each cell has a certain probability of dying, and that probability doesn't really change very much over the course of a treatment. It has to do with, like, at a microscopic scale, does the chemical reach every cell? Does the heat get absorbed by some cells so that it doesn't get to others right away? Things like that ultimately lead to these probabilistic situations. So the big take home from that so far is that killing microorganisms is not instantaneous. We have to think about the timing. And there are several different factors that control this. So the first one is, how do we define what is dead? Do we need to kill every cell? Sometimes we do. In a laboratory setting, when we want to make a bunch of petri dishes for growing bacteria on them, we want to make sure they start off completely sterile. So we have to make everything completely sterile. A hypodermic needle that you're going to use in a clinic has to be completely sterile. But your kitchen sink doesn't need to be completely sterile. You just need to make sure there aren't any pathogens in it. And so those would be different definitions of dead. If we start with a higher population, it takes longer to reach the low threshold we're aiming for. So every time you multiply the starting population by 10, you add another decimal reduction time to how long you have to expose the microorganisms. And then the decimal reduction time itself, so the time it takes to decrease the population by a factor of 10, that time depends on how sensitive the cells are and what type of agent we use. So you could imagine endospores are not very sensitive to anything. So it takes longer and more severe treatments to remove endospores. Some cells are extremely sensitive, so it doesn't take much time at all to kill certain types of cells. So we have to think about, what are we trying to remove? If we're trying to get sterilization, we have to remove endospores. And then, what type of agent do we use? So these are graphs from your textbook that illustrate these topics. So this shows the effect of the population size, the starting population, or the load of bacteria. This is a logarithmic scale, and this is a linear scale of time. So if we start at 10 to the 9th bacterial cells, it takes a certain amount of time to reach whatever threshold they were setting. So if we look at this scale, this is kind of silly, but 10 to the minus 1, that's 1/10 of a cell. 10 to the minus 3, 1/1000th of a cell. 100,000th, 1/10,000,000th. 1/1,000,000,000th of a cell is probably down here, and that's probably their target. So they want to be very safe. They want to keep going until they've done 18 decimal reductions. And I'm estimating that. I can't actually see that from the graph. And they're not making that point. They're just saying to get to this level, it would take a certain amount of time if you start at 10 to the 9th cells, but it would be quicker if you start with, that would be like 1 cell. It would be quicker. But the slope of both of them would be the same. So it's like the probability of any cell dying is the same whether you start with 1 billion of them or 1 of them. And well, 1 doesn't really make sense, but if there's like 10 of them, they would decrease, again, with the same decimal reduction time that the high population would start with. This down here would show the difference between endospores and vegetative cells. So endospores would have a much longer decimal reduction time. So it would take much longer to go from this high population down to a low population compared to vegetative cells, which would happen much quicker. And then this shows the difference between a microbistatic agent, so something that just prevents growth, versus something that kills. When you add the agent, you get killing for a microbicidal agent. Nothing dies when you put in a microbistatic agent. So make sure, again, that you can read this kind of graph. Now you might be asking, why are they showing these negative powers of 10? Why, if 10 to the minus 1 is 1/10 of a cell, what does that even mean? Well, it doesn't mean anything literally. I mean, you can't have 1/10 of a cell and it be alive. But this is like a safety factor kind of thing, where you think, how long would it take, if we're calculating the decimal reduction time, how long would it take to get down to 1 cell and then below 1 cell? You could calculate that expected time, but to be on the safe side, you would want to keep going longer than that. And so that's why they have these extra powers of 10. So here is a question. Can you read these and figure out the decimal reduction time? This would be a very good exercise for you to do. And on the next slide, there's a formula you can use to calculate it. But if I were you, I would pause this right now and see if you can figure out how to do it. Where you get, here's the information. A, if you're trying to figure out the decimal reduction time, A starts at time 0 and ends at time 24 minutes. So in 24 minutes, it goes from 10 to the 6th cells, or 1 million cells, down to 10 to the 0, or 1 cell. So how would you calculate the decimal reduction time? What I would look at is how many decimal reductions happen. Well, here's one. It goes from 1 million down to 100,000. So that's a 10-fold reduction. Then it goes from 100,000 down to 10,000. That's a 10-fold reduction. Down to 1,000, down to 100, 10, 1. So that's 1, 2, 3, 4, 5, 6 decimal reductions in 24 minutes. So by my math, that's 4 minutes per decimal reduction, or a 4-minute decimal reduction time. And that's the calculation I did here. And the formula here is decimal reduction time equals the total time divided by the logarithm of the initial population minus logarithm of the final population. And that logarithm stuff means taking this number as if it were just 6. So the logarithm of this number is 6. The logarithm of this number is 0. So it would be 6 minus 0. And that is essentially what I did when I was calculating it. And that's the beauty of using these exponents like this. You can just use them as numbers when you're talking about something like decimal reduction time or exponential growth. And that is plenty for this video. In the next slides, we will look at some other exciting things. So I will see you there.